Okay, everyone. Thank you for joining us today on webinar. We have a lot of different topics, a lot of different hosts. My name is Mario Dodić. I'm from HVAC Education Hub, and I will start with approximately 10 minutes of explaining my own installation. So regarding topics, part one will be I will explain my installation here and how efficiently it is to run it on -15 outdoor, because this winter was really cold in whole Europe, everywhere in the world, but in Croatia was like -15, -17. After myself, Nigel from ESBE will explain how to size a valves, a little bit about ESBE valves, and then Damon Blakemore with case study about cascade system and something more complex. After that, this will be like first 30 minutes. After that, part two will be panel with Darren from ESBE with us also, but Nathan Gambling and Richard Burrows will join us regarding different topics from water regulation and heat pump in general. Let me start with my installation. So first, I want to show you a little bit about the house and office itself. It's like 40 square meters, but it's really poor building. You will see here, let's say windows are PVC, it's new, but uh, for roof insulation is almost nothing here. Half of the office has something, and you will see the wall, because building itself is really poor. It's like 60 70 years old, but with really poor, without proper insulation. You will see here how wall is like falling apart. So this is the probably the worst case building what you can have, and still heat pump is running efficiently. So first thing always is heat loss. So a lot of people have assumptions about heat loss, but I will show you how important it is to have proper heat loss calculation. So here you will see a little bit about materials, U values. So you will see window. This is bathroom. Bathroom is the worst one. So you'll see U value is like 5 watts per square meter in Kelvin. This is really poor. Walls, brick, some of them have some insulation, some of them no, but really poor building, and roof and floor insulation. Here you will see something interesting. I did door blower test. So door blower test is when you want to test your building under 50 Pascal pressure, and I have 15 air changes per hour. If we calculate that, this is approximately 4 air changes on regular pressure, so 4 Pascal. This is really poor. In my calculation, I put 1.5, so not like 4, because I did some measurements here, but actually really poor values. And with this one, you can have more accurate heat loss. I put design outdoor temperature -6.7. Actually, Zagreb is usually people are putting -10, -15. I put -6.7, like a little bit conservative, and 3.5 kilowatt is heat loss. You will see here how some rooms are better, some rooms are really bad. So let's say bathroom, kitchen, this is without insulation, but in overall 3.5, so 40 square meter and 7,000 kilowatt hours. This is approximation for uh, heat what needs to be delivered to this office. This is first step, so always heat loss. With heat loss, we are going then to flow rates and pipe sizing. So flow rates, usually we are using delta T of 5. Depending on manufacturer, you can play with delta T, so you can have higher delta T, lower flow rate. On my unit, I have from 3 to 10, and then you will see how different is flow rate. So for example, if we are using delta T5, I can have 10 liters per minute. But if I put delta T7, I can go with 7 liters per minute. So with lower flow rate, we can go with different pipes. So this is important, especially if you can play with this on your heat pump. For me, delta T5 is also good, but just to show you, pipe work 22 millimeters from outdoor to indoor, and 2 radiators. So 22 everywhere. It's like approximately 40 meters of pipes, and at first you will think you cannot go with 22, but I put everything in calculation, and I will show you how this works in reality. And then after you are done with heat loss calculation with pipe sizing, you need to calculate each radiator. So each radiator has some heat loss, flow rate, heat output. This is what I have here. This is the same like you have on under for heating. Guys from UK will know flow regulating valves, and you can set up and balance every radiator on the heat what must be delivered. And the outcome is this. So the outcome is uniform value on radiator. You will see here, I think it's, yeah, January, it's really cold outside, so 34 approximately, but whole radiator is heated properly. So without balancing, you cannot do that. Here I have, let's say, 10 minutes, so I'll just jump on the topics just to show you some different things what probably you don't know until you test it. For me, it's good because it's in my office. It's only heating source in the office, but still I'm testing it because I want to see what is going on. So we always want to design to calculate everything correct, but commissioning is usually also misunderstood because with commissioning you can have really different values. I will show you now. So this is when outside was minus 15. You will see here 33 or something flow temperature, and you will see here in 24 hours below zero. So from -2, -3 to -15, COP in this full window was 2.9. So still, no matter how good is the house or not, but if you design, install, and commission the system good, you will have good data. And here you will see just what is the measures here, because here is I didn't install the sensor here, so 22 inside. Still you will see here also hit, let's say 2.2 kilowatts. So I calculated 3.5 on -6, but even on -15, because 24/7 is working, I have really good values. And what I want to show you now, I think I am now at the end of my part. Here you will see, I will just start this screen recording, how room influence on controller can have high impact. So you will see here, let's say the outdoor temperature is the same, but here at that point, I changed the room influence on controller. So I changed room influence, so indoor temperature will have higher influence than outdoor. And you will see here how this changed consumption. So curve was going up, not so much, like a few degrees, but consumption was like 200 or 300% more. You will see now on the lower part. So from 300 to 8 or 900 watts of electricity. So this was also for me strange, but I then talked with the guys in Bosch, and they said, yeah, you need to go inside of thermoregulation. So this is always my advice to everyone working and commissioning heat pumps. Try to be comfortable with your manufacturer, because not every manufacturer is different. Everyone has some specific parameters where you can have really poor COP. So today I'm testing something, outdoor is +16, but values are not so good like on -15, because I changed some parameters, and this is like you can have 100, 200% difference if you change some parameters. So try to be comfortable and try to learn manufacturer what you are installing. And this is also, you can see here, so 1.6 from 3 or 400. So again, room influence was here really big. This is all for me. I think I'm on time. Darren, you are now, sorry, Nigel and Darren together, but Nigel will take a stage.
Yeah, thank you very much. I shall share my presentation. So this year we're celebrating 120 years at ESBE, been a manufacturer of valves in Sweden for 120 years. So this is probably the most important bit I want to get across, is that we've got a dedicated UK technical line. If anyone's struggling with any valve selection or struggling how to set up or fit our valves, then I'd encourage you to get in contact. Obviously, I've got 10 minutes to get through quite a bit today. We had a previous webinar where I had a full half an hour, and obviously there's a recording of that. So if you're going to find out any further information, I suggest going to find that. We've got links, just contact us, or if you search for it on YouTube, it's pretty easy to find. So I'll start off with diverting. This is primarily what our valves are used for in domestic installations. So we have 3 different main types of valves that we offer for diverting. This is kind of the spring return valve. Some people call it ball valve, but it's not really a ball valve. It's a rubber ball moving across a can, which blocks the different ports, the A and the B port. And we'll come on to different properties of that. This is what we're famous for. This is our gold standard product. It's our rotary valve, and within there it's got a shoe, and that shoe kind of blocks off the different ports as it rotates around. We'll come on to that mechanism slightly later on. And the third type of that main type of valve that we offer for diverting is a motorized ball valve. And it's a ball with, it's actually got 4 ports in it, but it's quite complex the way it rotates and opens up the different ports as it rotates by the motor. Now, all these valves have different properties. Bottom property is KVS. Some of you may have heard of that. That's just a measure of the resistance of the valve, the amount of flow you would get through it for a set differential pressure. So you see that they have different characteristics. That spring return valve on the left has a lower KVS. It has more resistance through it, whereas the middle rotary valve has very low resistance through the valve, and the motorized ball valve somewhere in between. Now, there's another property, which is the differential pressure that defines the valve itself. And you'll see that varies across the different valves. And you'll see that it's a massive differential pressure across the motorized ball valve, but we wouldn't, there's an asterisk there, you see, but we wouldn't really recommend it above 200 kPa because you just get noise through the system. Now, what does that mean? What does that differential pressure mean? So if we have a heat source with a pump on it, and on this example, if, for example, we're in on heating mode and we close off the hot water side, and so we've got the pump running at Y, and then it's going through to the heating at X, and you have very little pressure at the hot water cylinder, call that Z, and so the allowable differential pressure will be the pump minus the pressure at the cylinder, that's Z. Sometimes it's called shut-off pressure because it's the pressure that the valve will close off against. So that's why we recommend those 2 valve types for a heat pump installation, because it has the heat pump's running at a higher flow rate, a higher differential, a high pressure. So a higher differential pressure rated valve and a lower resistance is more suitable for heat pumps. If anyone rings me up and asks which valve should I use, they're the 2 that I offer. So it can cause a bit of confusion out there because this is how a traditional diverting valve is configured, with the heat source coming in through, some might call it an A-B port. I would call it a branch. And then it's diverted between the 2 runs, between the A and the B. Now, our motorized ball valve, we call it an MBA, that has the same configuration in that you connect your heat source to the branch, and then we divert in between the hot water and the heating on the run ends. So our rotary valves, and this is where some confusion when you're not used to using our rotary valves, because we have different configurations of rotary valve. And it's these 2, the 130 range and the 330 range, which is piped in slightly differently, in that the heat source comes in from one of the run ends, and then you divert in between the remaining run end and the branch. That's our 130 range. Now 330 range. The 330 range has a lower resistance. It has a high KVS we produce. And the 230 range has the same configuration as what you may be used to for a spring return valve. Okay, when we move on to mixing, I always suggest we use our 130 range. It's configured in that way that you're mixing the flow coming in from one of the run ends, mixing with the branch end to come to a blend. You see that image on the bottom right hand screen side of the screen kind of marries up with the configuration of the bottom left, and they've got hot water coming in through one of the runs. You'll see there's little shapes actually on that illustration of a square, a circle, and a triangle. So obviously we've got hot coming into the square, and those shapes are actually stamped, they're embossed into the brass body themselves. So if anyone follows us up confused about how to pipe in one of these valves, first question we'll ask is what valve have you got, and B, where are you connecting your heat source, and C, where's the blend coming out, so we know it's all piped up correctly. The other, so we've got different codes, different figure numbers, and people are a little confused what they all mean, but that, just to let you know, that final number there, a 1 is a female BSP, the 2 is the male BSP, and the 3 is the compression version. So that's a bit about different styles of valves, particularly in diverting. But when we come into mixing, right, this is important because people tend not to understand it. It's important to size a valve for mixing in order to get what's known as good valve authority. Good valve authority is when you match the pressure loss across that valve with the pressure loss across the circuit. There we show an underfloor heating circuit. So good valve authority would have the pressure drop across the mixing valve identical to the pressure drop across the underfloor heating circuit. Why is that important? That's important so that we're using the full range of the valve. If you imagine if the valve was oversized, it would open up to let a little bit more heat through, but it would let far too much heat through, and it would overheat the system. The valve would instantly close, so we'd have the valve, what's known as hunting, that would be opening, overheating, and then closing again. So it's really important that we size the valves correctly. I'm just going to come on to how we would size them. That's why, if you look in our catalogue, in that red box there, you'll see there's just in the 1/2 inch valves there's 6 different variants, each with a different KVS, a different resistance through it, so that the valve can be matched with the resistance through the underfloor circuit. And I think I shall now come on. So we've got an app. I'll just stop sharing that, and this is going to cause more technical woes. So I'm going to just switch to a different camera. So on the open screen of the app, we've got different models. So this is our main model. I'll concentrate on that VRG 130. I'm conscious I'm running out of time, so I'll whiz through this, but I'd really encourage people to download this app. It's so useful to understand A, the function of the valve, but B, how to size the valve. So if we click on that VRG 130, it gives you 2 different options. We'll put on the function, we'll click on that, and here we see an image of a cross section of the valve, if you will. And if you slide your finger across the screen, it shows the shoe moving within the valve. So you can imagine which parts are being blocked as it rotates around. So it's really good to understand the function of that valve using that. But this is where it really comes into its own. When you're using it for mixing, this is how we do the sizing. So there's a calculator button, and we need to fill in 2 of those 3 parameters. So if we've got so we'll take an example of 2 litres a minute, which is 0.12 cubic meters an hour of the flow rate, and we've got a 5 degrees temperature difference. It gives us 2 alternatives of KVS values to select, and it gives us the product codes for the alternative 1, which is the best option to go with, the optimum KVS. It gives us product codes, the connection types, and everything in there. So I'd really encourage you, if you're doing a mixing, to use that for use that for your sizing. And I think I've run out of time. I had plenty more to go through, but I'll share
We
my
can send the
presentation again.
people, yeah, we can send the people link from last webinar if someone was not here, where you
Yeah,
dive more inside.
see, that's everything I was going to go on. But here we go on to Damon, who's going to present some of his case study. I think Damon's on the call.
Hi everyone. What I'll show you is a recent job that we've nearly finished on a big property in Sheffield, which was close to 2,000 square meters. Old property, solid stone that were built from like late in 1800s. We had an extra floor and observatory, a basement, a big glass fronted atrium at side, what's housed a big solar battery, a big pool house as well. So they were having biomass, but they had a bit of a fallout with the contractor and they wanted something different. So they come to us and it were a bit out of my comfort zone, where I like to be. I've never done anything as big as this. So we fitted three 20 kilowatt heliotherms, R2 90 units. There was two 800 litre cylinders. We've got four 450 accumulators because we've had to size the full house load. There's only four people living in this property. Husband, wife, two young children. But he wanted to have full load covered for the full house, which made it challenging. We've run it from a full KNX system internally. So because the house is so vast and because we only wanted to load one cylinder at once, he's linked it to his own automation. So depending on what rooms they're in, we can pull and load the rooms. His MVHR comes on. Is one cylinder he'll use. There's 5 secondary return pumps that are pulling to different points in the house, depending on which part of the house is lost. So it was quite challenging to be able to deliver all this. There's two units here for the house. So the house heat loss coming at close to 70 kilowatt. This job was already ongoing, so they'd already had the underfloor done. Everything was 150 mil centers everywhere. Like no matter what floor finish, no matter what size room, it was not done great. So we've had to try and work backwards from that. And on a project this size, that's been quite a bit of a challenge because it's already in the floor, it's already concreted, screeded over. So we've gone with a 850 litre a buffer. I don't know if there's any more slides that we can move to with this plant room and whatnot, but 850 litre buffer. So this is the hybrid bit for the pool. So there's a gas boiler that's going to the pool there. IM expansion valve. We've used Kingspan throughout on the 20 mil insulation all there. This is down in the basement. And you can go to it next. Oh, just on the right hand side, that's the heliotherm control. Just there. So the right hand side there, that's the left hand side, that's just the pool plant room. That's not fully up and running yet. We're back to finish that just mid March. But on the right hand side there is where we come in. So we've got 42 mil lines from both heat pumps through. Pumps are on the returns going back. ESBEs are on the floor there. They're the VRG 131s, the 1.5 ones. We wanted a good KV value on them, and something that would divert well. We've got the Calefe XF at the bottom, which are 1.5 units, which you can also set your KV value on, so you can use them as part bypass. So even though they're just big and the house is vast, there's a lot of money. We wanted to still make it as efficient as possible. Lower pump power, better performance, lower cost for customer. That's one of the reasons why we're using KNX as well for that secondary side. Because good performance is good, but on something this vast, there's so many kilowatt hours that we could save. So only eating what we actually need, only delivering what water we need is key to making this like a sustainable project for that. You can go again, Nigel, if you want. So they're the 200 litre cylinders there. Now these are piped off one heat pump each, so each one does its own cylinder. So depending on what we want and when we load shift to these through that, they run a Legionella cycle once a week if it's not being used. And then we've got motorized RAS-approved valves at the back that just open and close depending on what cylinder is on. Same with the secondary return, just so it doesn't pull through the other cylinder. The challenge here was actually, which I didn't find out until this, is that you can't use one combi block. You've got to use two combi blocks because to G3 states that if they're not piped in series, if they're piped in parallel, then they're classed as separate cylinders. You can't class them as one unit. So that's why the pipe runs up the left and comes across quite unsightly, because I were just going to pipe it in one and come out with the other. So we've had to use separate discharges, separate combi valves, separate expansion vessels to satisfy that at that point. You can go on again. Water quality, we have filled Demon fill, so running through the Alexion resin to lower that conductivity, raise that pH, take all the hardness out of there because there's a long life on the system. We've also, for oxygen control, we've also got a reaction tank, which is on a bypass on the other side of the buffer. There might be a photo of that, I'm not entirely sure. So that's running as a bypass, and it's got an anode in there, which is just water chemistry, which I got through a flush, and we're just removing that oxygen in a national process through that, just to keep the system longevity there. They're all the secondary return pumps that are running to different parts of the house, depending on which part of the house is being used, because hot water wastage from that is, temperature from that is crucial as well. So we've got minimum losses there, and we're only taking it to bits that are being used, and when that is. I think there was a question there, what just popped up. I liked the Heliotherm. I think they're a good unit. The instructions come in Austrian, which made it quite a German, should I say, which made it quite a challenge to understand. But simple to turn on, and commissioning process were pretty simple. They're running pretty well. They were turned on end of October. They've been running at just over 400% since then, and delivering that. Like I said, the heat loss was a little bit. They had 44 kilowatts of ventilation loss, infiltration loss on there. So when we went back in, we've had sensors in rooms. We've took in solar gain, we've took in shading, wind direction. There's been quite a lot of a specialized heat loss contractor that we got in. We managed to get it down to just under 40 kilowatts, so we can provide full heat load just through them too. He's also got full VRF set up, what he can bring in times when it goes lower to help with that. Expansion, we've got 100 litres on the heating. It's designed at 45 degrees, but we've been running it at 40. And what we've also got is, through his Kinetic system, we can load shift, so we can load the buffer up to 60 degrees, 65 degrees, and then I've got a fixed blending valve on the secondary side, an L-Technic one, which is an high flow one. And on that, I've set that to 45 degrees. So if we do store higher at lower tariff times, then we're able to utilize more storage out of there because we're blending down. The only thing while I was doing it, what I come across is, would I be more beneficial using a weather compensation and a fixed blender on the secondary side from the buffer for the house, and having that just pulling off, because in times of high charge, when it's 65, I'm not going to be able to lower that temperature to below 45. It's going to be fixed. Whereas if I had a secondary, it wasn't something I think about until after the job, but if I could from that point, I wouldn't need to run weather comp then in times of low tariff. I could run fixed temperature at 65, utilize that buffer up, but I might only need 33, 34 on the secondary side. So at that point, I can then maximize more kilowatt hours from that buffer, and maybe I should have oversized that buffer a little bit more, maybe 1,500 litres to utilize that. But that was just something that changes we get over the job. There's nothing wrong with how it's done. It's just always looking at ways to improve on what I've done wrong on every job. And I think that'd be the biggest improvement there, to use weather comp on the secondary and use fixed flow on the primary in times of low tariff, which you could do from his KNX system. So I do a lot of information there. I kind of sporadic with it, but
Thanks a lot, Damon. Damon was being a little bit modest there. That's actually my house. For your benefit, I'm Darren Myers from ESBE Limited in the UK.
Right.
A lot of people see I've got a face for radio, and maybe not for TV. So I'm going to introduce the people here who we've got. We've got Damon Blakemore Renewables, who would you see, HVA. I think the term that really pulls Damon together is not all heroes wear capes. Alongside them, and this is where we see if the ITs work correctly, We have Rich Burrows, so I'm hoping he's in here. He's the most honest pirate I've ever met in the industry and on a personal level. He's a voice of renewables and owner of Mid-Wales Plumbing and Heating. Alongside of that, we have the Right Honourable Nathan Gamblin. Better Talk, we know him of his podcasts, and now he's the founder of the Guild of Heat Engineers. Of course, we've got Mario and Nigel. Okay, so I've got some questions which I'm going to throw out. These haven't been rehearsed, so this might be quite interesting. I will start very softly, and then we'll get a little bit more interesting. So this goes out to Mario and Nathan. Which is most important, design or commissioning of heat pumps?
I explained my case. I can say design because if you are wrong with commissioning, you can always change parameters. But with design, you cannot change. You cannot change anything. But I think a lot of people are missing good commissioning. As I explained, especially Damon has also experience with different manufacturers, especially German manufacturers. They have really advanced control, which is sometimes good if you are a nerd. But if you are not familiar with this, you can have very different values. So I think design is more important, just because you cannot change it usually.
Mario, thank you. Nathan, are you in our audience?
I am indeed, and that was
there he is.
That's quite a good answer for
Hey,
Mario.
mate.
Can you hear me?
Yes.
Yeah.
Yeah,
Damon
I see you.
So yeah, so what Mario said there was interesting. So the design, once you've got your design, you're kind of set in stone a little bit. I mean, back in the day, design was obviously done. I'm going back in the day, by building services engineers, and then you'd fitters would go out and fit stuff, and then you would have commissioning engineers, and obviously commissioning is quite important, and it's not always done right, but you can get it done right. You know, you can have people go out there and do it right. And like Mario says, if the design's wrong and it's been installed with a bad design, then you got problems sometimes.
If you actually want my 2 pennies, I think the design's everything. I think you can fix in the commissioning. But that's just me. What do I know? Okay, Damo, next one's for you. What are the most common mistakes that you find when installing heat pumps? What can we tell the audience to make it a little bit easier? I'll give you a starter. Heat pumps are really heavy. Get something to move them.
Yeah, they are. Mistakes. I think there's so much that can go wrong. You have your 4 key areas, which are your initial heat loss and specification. Your design, your installation, and then your commissioning. I think there's so much that you could do differently over them depending on how you work and the way you adapt to that. That you do any bit of that wrong and it can fall out a sink and it cannot work properly. So it's kind of hard. I'd say pipe sizing undersized is a main one. Adding needless buffers and secondary sides when they're not. And I'm not talking about just going open circuit. I'm just talking about going direct from one pump. We seem to be in a way of this one set has to fit every single house, where every single house is different. Every single house needs a different approach. You should design to the house and the customer. And you see it from manufacturers, it's just one schematic that goes to every single plot, every single job. So I think that the main thing is not designing to what you require for that project.
Thank you. So I would say, again, it means absolutely nothing. But I think planning is everything. But that's just me. Okay, Rich, this is for you, my pirate friend. What are the biggest challenges from transitioning from gas boiler installs to heat pumps? Richard, I hope you're out there.
I am indeed. Hopefully,
there we go.
So the biggest transition is the fact that loads of guys have just been throwing gas boilers at walls for so long that they don't fully appreciate how the difference of design between heat pumps and gas boilers differs. Until they go on courses like Kimbo's course or something like that, then you have a bit of a light bulb moment all the time, don't you? And you end up realizing that you don't know anything actually. So yeah, the biggest sort of the key elements are that obviously gas boilers run very differently. They're much more, I would say, much more friendlier to installer designs, because if you get a heat pump wrong, you can't go turning the flow temperature up to 70 degrees easily. Do you know what I mean? Where, you know, if you've got a gas boiler and you've designed it for 55 and it don't work, you've got a bit of redundancy there, haven't you, most of the time, because these things are, for the majority, oversized anyway. So so yeah, I mean, you know, you see it all the time. If you only have to go across the groups or the forums, don't you, and you can see hundreds and hundreds of installations that have been done incorrectly. And, you know, unfortunately, like Damo said, there's you know, one size doesn't fit all. But what happens is, on the heat pump side, is a lot of guys who fit in gas boilers decide to just go and buy a pre-plumb cylinder and a heat pump, and the pre-plumb's got one size pump on it and expects it to fit every size house, from the smallest bungalows to the biggest 4-bed mansions. You know what I mean? And it don't work. So, you know, it's as Mario's already touched on, and Nathan, you know, design's key. So that's, you know, if you don't learn the ropes, so to speak, about heat pumps, then the transition from gas boilers to heat pumps is going to be a very, very steep learning curve, shall we say.
Do you think that jumping in, do you think heat pumps are also normally oversized as well?
I think we get a bit bent up on the oversize and the heat pumps. I mean, if you look at the Open Energy Monitor statistics on my heat pump, then mine shouldn't work, because yeah, if you go on the oversizing point, then yeah, mine shouldn't work. So I've got a 12 kilowatt heat pump, which I had an MCS installer actually come out, and because I didn't fit it myself, but I did the design and all the other bits, but they had to sign it off. So yeah, he had to put a 12 kilowatt in, because that's what the numbers said. But actually, I knew, after years of running heat pumps and solar thermal, I got a solar thermal panel, and that heats my house most of the time. Do you know what I mean? And so I knew it wasn't a lot of energy required. And yeah, you know, if you look at the data off my heat pump, I think it averages about 4 kilowatts most of the time. So, you know, my heat pump's 3 times the size, and yet I can get it running. You know, I've had to accommodate it with volume. So I've had to increase the volume of the systems just to get the heat pump running longer at a lower flow temperature. But for the majority of the time, it runs very, very efficiently. And, you know, like I said, it's 3 times the size. That's not the case in every site, every place, because if you haven't got the volume, you're going to struggle there, aren't you, with your modulation? But yeah, I don't think I don't think it's as bad as people think. I think actually what Damon said before is it's more the issue of adding too many pumps in, or adding things into the system that you don't need, and then, you know, you end up fighting against those things, and that's where the inefficiency actually is, rather than actually the sizing of the heat pump.
Can I jump in? Just to jump in. I think the main issue with oversizing is that not everyone is Richard Burrows. So if you have this setup in different house, as he mentioned, without volume, without tweaking out, I think it will be poor. And also his heat pump, as I know, has really good modulation ratio. So what we are missing with oversizing, you can put, let's say, 30 or 40% oversize unit, which will be wrong if modulation ratio, let's say minimum, is not so good. But if you have good minimum value, sometimes it's not a problem to oversize, especially in the UK, because you have design outdoor temperature when you have the highest defrost around the 0. In Croatia is higher problem, because I showed you this winter was -15, but last 12 winters were not like that, and usually it's not like that. And if you size for -15 or -17, you need to go with really big unit, because there is really big capacity drop. And usually, I think here in our area is more problem of oversize than in the UK, and with this approach. So I think oversizing with bad design, and I will not say bad installer, but bad approach will be the issue.
I was going to add to that, actually, that my heat pump size was probably about -30. So should be all right if the UK temperature decides to go Arctic on us. But
like Greenland.
So I'll just jump in here. We've got a couple of good questions. So just taking from what Richard said, in the immortal words of Snoop Doggy Dogg, right? No, yes, fizzle. Mario keeps talking about -15. He's never been to Newcastle, but that's t-shirt weather. Anybody who knows me, I'm not one for dropping the bomb, but I want to drop the bomb now. So this is to all the panelists. So I'll just put my glasses on here. What do you think of the G3 unvented cylinder regulations for heat pump installations?
BS.
Damon, over to you.
Yeah, it's outdated, based on regulations and things years ago for high temperature to have them cut offs. Nathan will know, he promotes it a lot more than anyone, is that to satisfy building regs, you only need to get what's in the green box, which is done, if I remember right, it's prevent hot water from reaching 100 degrees. Critical temperature R290 is 96. Mario will probably get me on this. 96.7, maybe, I think.
Yeah.
So you're never even going to reach that temperature. So currently I'm sat with HPA. Nancy, Nathan knows again, is pushing for something to do with the HWA, so we can get some FAQs written in so that we've got clarity there from that. But it's, what do you need it for? If you're never hitting that temperature, why do you need a crappy spring-loaded valve that ball's going to come off? You've got a low KV value. You get noise every time it slams. It's going to be detrimental to the system. What? We're just so behind. So behind with times.
So from a layman's point of view, if heat pump's not going to get to 95 degrees, and people are worried about the system going off. Okay, so what happens when the electricity goes off with the gas boiler?
Electricity rules everything, doesn't it? If you don't got no electric, you ain't got anything, unless you've got a battery with a discoupled from system. It's
And that's just from a layman. I'm just good looking. Nathan, anything to say on that?
Yeah, I mean, the issue I think we're getting is there's some really good engineers out there, like Damon, lots of them, who are they're the people at the ground, they're the innovators, they're the ones, we're in a complex industry. Now, the regulations arguably are okay. So the Building Act 1984 established the building regulations of 2010, and they don't tell us to use certain things. They never would do that because that prevents innovation. And so the actual requirements, which are in the approved documents, people think approved documents are the regulations. They're not the regulations. They're mainly guidance. And a lot of the guidance has been written by manufacturers over the years. The issue is the certification bodies that are working with MCS, there's about 10 of them now. When they go out and audit work, they are auditing to guidance. And that's a bit of a problem because the best people out there working with heating systems are the engineers. It's not the auditors working for CB companies. Most of them don't really understand the systems people like Damon are putting in. So that they have to, by law, that they're governed by UCAS. That they're just ticking off their checkboxes. So if people are going a little bit what they think is deviating from the norm, which engineers are allowed to do, we're allowed to innovate. And that's an issue. And there's people getting pulled up on all sorts of stuff around G3 and other things as well. And it's a bit of a shame. So I think there are going to be some meetings going on. I'm going to be talking to some people and some people in the CBs about this, because you've got to give the engineers, as we're moving in the industry and we're innovating, and people like your Damons are innovating and everyone's learning what best practice is, the people doing the auditing have got to keep up to date with that themselves.
Yeah. Good. Thank you. Good answers, lads. Right. This is for Nathan and Rich. How could the government increase the uptake on heat pumps in the UK?
What was that, Darren?
How could the government increase the uptake of heat pumps in the UK?
You go first, Rich.
You know what? It's a tough one. I said this about three or four installers ago. I had a similar question on the panel, right? And I just said, look, you got two ways to go about it. You either fund your way into it, so you either give really good, because let's face it, $7,500 doesn't cover a heat pump install. So it depends what the agenda is really. It's like, do you want to fit low carbon technology? Because if you do, you need to fund more. Yeah, so you need to add more funding. But what we're actually seeing, because I drive an electric vehicle, I've just got a 380 80 odd quid tax bill through for my electric van, which pollutes nothing. Yeah, it does rip the roads up when I press the accelerator pedal all the time. Do you know what I mean? But doesn't do a lot. So you can tell already, like, anything green is already being taxed from, or shall I say, the existing green levies are already being taxed now, right? So it's very unlikely they're going to increase the 7,500 anymore, you know, in my opinion. So
that's quite interesting, because in Southern Ireland, I think they're at 12,500 for the grant.
Yeah, I said it needed to be about 10 to 12 grand. So that's where I said it needs to be if you really want adoption. But I mean, ultimately, it's slashing the electricity rates. As soon as you get electricity down to like gas levels, then it should instantly take off, shouldn't it? Because you're going to have a payback period for the majority of heat pumps, irrespective of efficiency. So, you know, you've got that. So that's, I mean, if the government really want to make change, get on top of the electricity problems we've got, isn't it? You know, and they keep promising like nuclear is going to solve it all. I don't think it will. I think there's a bigger picture than that. And yeah, I think that's the only real way to make sure heat pumps are adopted is get on top of the electricity prices.
Richard, thanks a lot. Anything you want to add?
Well, Rich has obviously mentioned the obvious one, the electricity price. I mean, these things are expensive for people to put, you know, air to water system. I mean, air to air can be a bit cheaper, but they're expensive things for people. People don't have money. I mean, and we talk about the transition as if it's got to be quick. I mean, it might be a slow trend. I mean, if you look at central heating when it sort of comes sort of popular in the 60s and 70s, you know, what my dad did we did have a central heating until 1981. You know, it was a slow movement to people switching from the gas fire or the electric bar fire in their lounge to have a full central heating system.
Yeah, I think I still haven't got central heating.
It might be a slower transition than we all think it will be, because, like I say, it costs people a lot of money. And you know, I don't know if the country's got a lot of money to keep throwing at grants. I don't know.
Steve, thank you for that. Right, I've got about 2 or 3 minutes left before I hand over to Mario. I've just got one quick question from my point of view. This is to all of you. When you're doing a heat pump install, do you prefer radiators and underfloor heating or underfloor heating? Please tell me what your thoughts are.
I prefer underfloor you just feel you get better heat when it's through your feet, you know, but sometimes, depending on what you've got upstairs, it's hard to fit that underfloor. So a mixture of underfloor and rads is pretty good. You know, you could look at wall heating or ceiling heating as well if you wanted cooling. So yeah, I don't know, you know, as long as your home's comfortable, then I haven't really got a preference.
Anything from anybody else?
I can say underfloor.
I'm just thinking about the refurb market, because there's all these radiators out there, and these plumbers have been fitting radiators the same size as windows. And I think if the market's going to kick off the way it should do you think radiators are a viable option?
Yeah, radiators will always be viable. I mean, it's just another emitter. It's just a surface area of emitter. I like underfloor heat. It's comfortable. If I'm out drinking with Damon and I end up crashing out on the kitchen floor, I'm laughing if it's underfloor.
You're lucky you got the kitchen floor, Nathan. You're lucky that you got the kitchen floor. If any,
I think there's a bit of a fear from the general public that you're putting a heat pump in, you're going to have to put massive radiators in. I think it's a bit of a blockage for people putting a heat pump system in.
Thank you. It is a really good point. Right, before I hand over to Mario, if you've got any burning questions, you can contact us all. There's a chat going here. Email addresses are available. You probably know the people on the panel. We are all here to help. Mario, my time is up. I want to thank the audience for listening and taking the time out of your day, because I know you're all busy. Mario, I'll hand it back to you.
Yeah, just 1 minute for the end. I want to say thank you to everyone, to you, to the guys, to the people. I can see 70 people joined and 160 registrations. So really good. I will just spend, let me just spend a few seconds just to show you something. I'm just finishing. Let's say this is almost done. Completely new platform. Damon did, and few of you also did this introduction course, but now it's like full full course like let's say Hydronics masterclass with interactive assessment when you can drag and drop everything. I also put what we discussed, commissioning, troubleshooting. This is really important. I will send to the people, so just to see, like, the idea is Nathan is talking a lot about that. So science of learning and gamified learning. So learning is usually boring if you are just putting PowerPoints, but I try to make this like a play. So this is just for people to see, and I will send more details. So do not spend your time here, and I will just spend 30 more seconds with quick feedback. Just 2 questions, so just for people to rate the webinar and to answer if they want more webinars like this one. So just to see the feedback, because it was, let's say, it's challenging to have 5 or 6 people on board and with IT stuff and everything, and we are on time. So I think from my perspective, we did quite good, but just for people, this mix of education and panel, it's like, is it a way to go or no? Okay, poll is done. Thank you, everyone. I think we are.
Thank you.
Thank you very much.
Yeah.
Thank you. Thank you.